All right, let's talk about cylindrical coordinates. All right, remember when we're dealing with regions that are on the xy plane, we talked about polar coordinates. Think of cylindrical coordinates as an extension of polar coordinate from a region that's just a plane to a region that's a solid. Now, if you remember, polar coordinates, the conversion is x is r cosine theta and y is r sine theta. Now we're going to add z, but z is just going to remain as z. We're not going to convert z to anything. So for instance, let's look at a region, this region B, okay? The region is a cylinder. Think of it as a cylinder whose radius is 1. The radius of this cylinder is 1 over here. And the height of the cylinder is 2. So along the x-axis, it goes from 0 to 2. Okay? Remember that. And along the radius goes from 0. If you want to cover the whole region, you'll be thinking of circles whose radius go from 0 to 1. And then if you want to cover the whole circle again, you're going from theta is equal to 1 all around, which is theta equals 1 to theta equals 2 pi. Hence, if we extend our polar coordinates, which used to be just r and theta, polar coordinates is just r and theta. If we extend it by adding z, right, then this will become the description of this region B, right? So in this video, I already wrote some things down. I started all over and then I made a mistake and I wanted to start all over again. And I'm just using what I wrote before. So that's why I already have things set up. So I have polar coordinates. We have r, theta, z. Polar coordinate, we have just r and theta. So cylindrical coordinate, we have r, theta, and z. So for that reason, r goes from 0 to 1. I already explained 0 to 1 here. Theta goes from 0 to 2 pi, and z goes from 0 to 2 for this particular solid, okay? This is just an example. Now let's do more examples. Assume you want to plot the point 2 pi over 6, and 4. So our r is 2, theta is pi over 6, and z is 4. Okay, we want to plot it in the x, y, z space. So I'm going to start by plotting r and theta on the xy plane, okay? So if we go theta pi over 6 is 30 degrees. So we're going from 0 to 30 degrees, pi over 6. And then we want to extend 2 units outside. So this is 1 unit, and this is another unit. So this is our point here. This point already is 2 pi over 6. So all we have to do now is come over here, plot 2 pi over 6 on the xy plane. So this is what we already have. 1 unit, 2 units, okay? Not too perfect, but that's okay. So this is pi over 6, this angle, and this point is 2, right? So this is 2 pi over 6. Now we have to move it up 4 units. Let's move it up 4 units. I'm going to use, let me use green. 1 unit up, another unit, and then another unit. So this is our point right here. This is our point. Our point is 2 pi over 6, 4. Okay? All right, so that's one example. Another example, or a bunch more examples. Let's see. Want to sketch the following regions. All right. The first region is r theta z, such that theta is equal to pi over 2. Such that theta is equal to pi over 2. So there's no restriction on r. There is no restriction on z. The only restriction is on theta. That makes our job a little bit easier. So we have x, z axis, y axis, and x axis. No, x axis here, and then y axis there. All right. So we're going, if we start from the x axis, pi over 2 is here, right here. So this is pi over 2, 90 degrees. So all we're doing is we're running along the x-axis, along the y-axis. There is no limit. No limit along the y-axis, no limits along the z-axis. What do I mean? I mean that since we have no restriction in the description of the function, or in the description of the set, this set is just the whole plane, the whole of the z, y plane. That makes sense. That is crooked. So this plane, and it's infinite, it continues, goes down, so it continues, extends all over the place, doesn't stop. So this particular example just turns out to be the YZ plane. All right, let's look at another region, B. This is a region R theta Z, such that R is equal to 1. So there is no restriction on theta. There is no restriction on Z. So if that's the case, we are simply just looking at a cylinder of radius 1. So we want a cylinder of radius 1. No restriction on theta. So that means theta goes from 0 to 2 pi, and z goes from negative infinity to infinity. So the only restriction here is 1, 1, and so forth. So this is an infinite cylinder. Infinite cylinder, it continues up and down. Infinite cylinder of radius 1, running along the z-axis. This is y and this is x. Now let's look at another one. R theta z, such that z is equal to 1 such that z is equal to 1 minus r, and r is between 0 and 1. Okay. All right, so this needs a little bit of thinking, but let's see how it goes. Let's sketch our axis first. Okay, so think about it. Let's start with z. When z, think about this. When z is equal to 0, r is equal to 1. So we're going to have something like this. When z is 0, we have a circle of radius 1. Now, when z is when z is say 0.5, what do we have? We have a circle of radius 0.5. Okay. And now when z is 1, what do we have? When z is 1, then r is 0. So we have a circle of radius 0. So what this means is that as we're running along the z-axis from 0 to 1, the radius is reducing. So we end up with a cone like this. Okay, so that's our region. Again, this is the x-axis, that's the y-axis, and this is the z-axis. All right, now let's do some triple integral examples. Some examples. Call this example 3. Let us find the volume of the cylinder x squared plus y squared is equal to 1, bounded by the plane z equals 0 and z equals 2. Now this is a cylinder y. It's in 3D and it doesn't have the z variable. Since it doesn't have the z variable, it is just a cylinder parallel to the z-axis, running along the z-axis. A cylinder that runs along the z-axis. Okay, I'm gonna move this down a little bit. Maybe move it up, why not? So let's sketch our cylinder. It's the same thing I've been sketching all along, so. All right, so this is z-axis, y-axis, x-axis. So this is our cylinder, and the cylinder is a cylinder of radius 1, right? 1, because this is a circle of radius 1. So just a circle of radius 1 that runs along the x-axis, along the z-axis from z equals 0 to z equals 2. Now, we're looking for the volume. If you're looking for the volume of a cylinder, all you have to do, I'm calling it B. Let me call it B. All you have to do, this volume is just the integral, triple integral over B of 1, right? Times dz of 1, no. dv, okay? 1 dv. Remember, where our region of integration is B. But when you're looking for a volume of a solid, all you have to do is to calculate a triple integral over that volume, 1, the function 1, dv. Now let's look at our b. What is our b? B now is the region r theta z. R theta z. R goes from 0 to 1. Theta goes from 0 to 2 pi. And z goes from 0 to 2. Okay? So our volume that we're looking for is, let's rewrite this integral here. So the integral, let's start with z. Z is going to go from 0 to 2 of 1 dz. All right? And then r is going to go from 0 to 1, and theta is going to go from 0 to 2 pi. But remember, we're doing polar coordinates, so we can do dr, d theta, but since we're doing polar coordinates, cylindrical coordinate is just an extension of polar coordinate. You have to put the little r there. Okay, you have to put the r there. Okay, so in this case, we can see that this is triple integral, but at the same time, we can separate these integrals, actually. We can just go 0 to 2 pi, bring the d theta here, and then we can go 0 to 1 r dr, and then we can go 0 to 2 dz. Okay? So compute each of these integrals. This gives me 2 pi, this gives me 1/2, this gives me 2. So this, my answer is actually 2 pi. Okay, so try it yourself, solve each of them, solve this, and solve that, and multiply it together. All right, let's look at a problem that we looked at the last time on the previous section. We looked at this problem, but we didn't finish it. Let's evaluate the integral square root of x squared plus y squared dv over E, where E is the region bounded by the paraboloid z equals x squared plus y squared, and the plane z equals 4. All right, so let me see if I can grab what I sketched in the previous section. Let me see if I can find it. All right, I think I can find it. Yes, this is what I had. This is what we had in the previous section. Okay, I am just gonna copy what we did, and then I'm gonna copy and then come here. All right, so when we didn't have cylindrical coordinate, this was what we did. I'm gonna box it in pink, tangled up in pink. This was what we did. Now we have cylindrical coordinate. We have to redo it. We need to redo this because we stopped here. Remember, we stopped here and I asked you to think about it. Okay, this is a little bit interesting, a little bit more complex, but with cylindrical coordinate, we can make it a little easier. All right, we described our E in Cartesian coordinates, and then we set up an integral, and then we have the integral here. But now we can redo this. We can rewrite our E. we can redescribe our E. Remember, this is our E, the region E. All right. E is R theta Z. We're going to start with Z because Z has the most variables. So Z goes from the plane. Z is between x squared plus y squared and 4. X squared plus y squared. Think about a circle. The equation of a circle is x squared. So if you get a random circle, think about any arbitrary circle around this region. Okay? All right? You don't know this circle. All right? But you know its radius. If you have it, if you want to describe it, you can describe it as x squared plus y squared is equal to the radius squared, r squared. Okay? So we're in polar coordinates and we're dealing with radiuses. We're dealing with r. So this x squared plus y squared is simply r squared. So we can write it as r squared and 4. And then r goes from 0 to what? Let's look at r. What does r go to? R goes from anybody want to help me out? Nobody's here? All right. Let's look at r. R goes from 0 to 4. R 0 to 4. And theta goes from 0 to 2 pi. Okay. Well, let's backtrack a little bit. So r squared, this is where z is equal to 4, and this is z is equal to x squared plus y squared. So z is r squared. So r has to go from 0. R has to go from 0 to 2. To 2. Okay. All right, so I'm going to set this up. We're going to go from, we have our E. We have our E, and then we have square root of x squared plus y squared. So, well, I want to convince you that x squared plus y squared is actually r squared. Let me convince you, because I did that really quickly. So I had x squared plus r squared. So remember that we have x squared plus y squared is going to be r cosine squared theta, r squared cosine squared theta, plus r squared sine squared theta, which is just r squared, then cosine squared theta plus sine squared theta. This is 1. And then we have r squared. Okay? So now let's go back to our integral. Our integral, which is now, I'm going to copy this. Copy. This is the integral we want. This integral now becomes, we're going to start with z. Z goes from r squared to 4 dz. Square root of x squared plus y squared is just the square root of r squared. So this is r dz. And then r goes from 0 to 2, and then theta goes from 0 to 2 pi. And then we have dr, d theta, but then we have to put the extra r there. So we end up with, we can break this up as little integrals. We actually can't, because we have here, we have this r doesn't allow us to break it up into small integrals, into product of single integrals. So, but let's start by doing 0 to 2, and then 0 to 2 pi, 0 to 2, r squared to 4, then r squared, then dz, dr, d theta. So I just set it up, and now it's quite easy for you. So if you keep going, you can do the first integral will give you r squared z, and then you plug in r squared. You plug in r squared, you plug in 4. All right. And then you still have 0 to 2, 0 to 2 pi, dr, d theta. So when you plug in 4 and r squared, you get 4r squared minus r cubed. No, minus r to the 4th, dr, d theta, 0 to 2, 0 to 2, 0 to 2 pi. And then you keep going. The next one will give you, if you take the next integral, you get 4 over 3 r cubed minus r to the power of 5 over 5. You plug in 0, you plug in 2, 0 to 2 pi, d theta. When you plug in 0, you just get 0. When you plug in 2, you have 8 times, you have, 32 over 3 minus 32 over 5. This is weird. All right, I will stop here. So you have 0 to 2 pi, and then you have d theta. So I want you to find out what that number is. 32. So it's 32 times 5 minus 32 times 3. All right? All over 15. Okay? And then this is theta. Then you plug in 0, you plug in 2 pi. So that is going to be 32 times 2. So you have 32 times 2 is 64 over 15, right? Theta. You plug in 0 and 2 pi. When you plug in 2 pi, you get 128 pi over 15. All right, I did this in a hurry. I want you to look over my work and make sure this is correct, but that's how we do it. All right. So another thing I want us to look at is spherical coordinates. Spherical coordinate is another interesting kind of extension of polar coordinates. Okay. So think about this. If we have a sphere, and we take a point on that sphere. So assuming the sphere is centered on the x, on the origin, at the origin. So let's go. All right. Okay. So if you have a point over here, think of this point, call it P. All right. So assuming on the XY plane, P makes an angle of theta, okay, with the x-axis. So P goes, let's do this. Oh no. Okay. Assuming this is where P lives and gets projected up there. And it makes an angle of theta. And then assuming also that P also makes an angle of phi. All right, with the z-axis. Makes an angle of theta with the x-axis, makes an angle of phi with the z-axis, and then its distance from the origin, call it rho. Rho. Then we can describe P. We can describe the points P using the coordinates rho, theta, and phi. Rho, theta, and phi. So the coordinates are rho, theta, and phi. Rho is its distance from the origin. Phi is the angle it makes with the z-axis. And theta is the angle it makes with the x-axis. And the conversion here is a little different. X is going to be rho sine phi. Nope. Rho sine phi cosine theta. Now, if you think about it, rho sine phi is going to be, if you want to calculate this radius over here, this radius is actually rho sine phi. I want you to think about it. I want you to think about how it comes to be, right? That's rho sine phi. Think about it. So this is your r cosine theta. So y is going to be r, which is still rho sine phi, sine theta. And then z is rho cosine phi, rho cosine phi. Because this height here is rho cosine phi. So this is the conversion we need. This is the conversion we're using. Okay. So this is a little bit different in that if you have a surface, if you have a solid, say E, your region of integration is E, such that E is rho let's do rho phi theta or rho theta phi. All right, let's go with rho phi theta. Sorry about that. Rho phi theta. It doesn't matter which one comes first, but by convention, phi should come first. That's okay. If you have a region that is described as rho phi theta, such that rho goes from maybe a function g of, let me not do that. Let's see. Rho goes from something to something. Let's just say that. And phi goes from something to another thing. Okay? Just stay with me. And theta goes from something to another thing. Okay? So that is how we are going to be describing our region. And I'm going to do an example and show you how this now works. There is some noise outside my window, and I hope you can. I am very sorry if you can hear that noise. but you shouldn't be hearing it. Whoa. All right. So this example is to evaluate the integral e to the x squared plus y squared plus z squared to the power of 3/2 dv. And where e is the unit ball. So it's a unit sphere, all right? And the unit ball is just x, y, z, such that x squared plus y squared plus z squared is less than or equal to 1, all right? Now, the first thing we need to do is to rewrite our e in terms of spherical coordinates. Remember that in the spherical coordinate, rho is the radius of the sphere. So if you have this sphere or this ball, the unit ball, okay, the radius is 1. The radius of this ball is 1. Okay. So rho goes from 0 to 1. Phi is the angle it makes with the z-axis. So phi goes from, sorry, this is phi. Phi goes from 0 to pi, actually, just 0 to pi. And now theta is the angle it makes with the x-axis. So theta can go from 0 all the way to 2 pi. So let's describe our E. E is r phi theta such that rho is rho, not r, rho phi theta, such that rho is between 0 and 1. Phi is between 0 and pi, and theta is between 0 and 2 pi. So that's our E, all right? So another thing I want you to notice, remember when we talked about a sphere, we said that the equation of a sphere is x squared plus y squared plus z squared. This is a sphere centered at the origin. It's going to be x squared plus y squared plus z squared is equal to r squared, the radius squared. All right? But in this case, the radius is rho, so we have rho squared. So now, what do we have here? We have this integral. Copy. So this is how we set up the integral in spherical coordinates. We start with the phi. We start with rho, actually. Rho goes from 0 to 1. And then theta goes from 0 to pi. No. Phi goes from 0 to pi. And theta goes from 0 to 2 pi. All right? So we have d rho, d phi, d theta. All right? Rho goes from, this is d rho, d phi, d theta. And I'm going to leave space for something. And I'm going to add it, and you're going to ask a lot of questions. But don't ask a lot of questions because I can explain in class. Now, we have e to the x squared plus y squared plus z squared, which is just rho squared. So this is e to the rho squared to the power of 3/2. Now I'm going to insert something over here that you must insert. Remember how we just add an r for polar coordinate? Here you have to add rho squared sine phi. In every spherical coordinate integration you do, you have to add that. Rho squared sine phi. Okay? We'll discuss it in class more, but just remember to do it for now. So now this is an integral that you can actually just pull around, and this one is you can separate everything. You have totally a function of rho, a function of phi. So we can start with theta. Theta goes from 0 to 2 pi d theta times the integral 0 to pi. We can bring out our sine phi d phi, and then 0 to 1 e to the rho cubed times rho squared d rho. And we can do this because the limits of integration are all constants, right? And we can separate the integrals. So the first integral gives us 2 pi. The second integral, what does it give me? It gives me minus cosine phi, and then 0 to pi, and then 1/3. The last one gives me, you have to use substitution to get 1/3 e to the rho cubed, and then you're going from 0 to 1. Okay, and I'll let you finish it up. But the answer I got is actually 4/3 pi e minus 1. So I want you to simplify this and get that. Okay. All right, I'm gonna stop here. Talk to you in class or the next video.